Can everybody hear me up there? Are we good? All right. People asked when the last day to submit readings is the last day of classes. So that will be, I believe, Tuesday, May 1st. Is that right? Maybe midnight of Tuesday, May 1st. That will be the last day to submit stuff. And of course, the rules still hold on only 2 submissions per day. Extra credits, again, under the same rule, 2 submissions per day. So wrap up all the readings and the submissions by the last day of class. The final exam will take place right after that. Maybe a day or 2 later, we'll have roughly about 5, 6, maybe 7-day window, just like for the midterm, where you can work on your exam for 6 consecutive hours. Your call when you want to do that. Same rules as the midterm, basically. Any questions about that? Okay. So last time we left off with the complexity zoo, which is a huge set of named complexity classes for time and space and other resource bounds. There's hundreds of named classes. As of the last tally, there's about 535 classes in this complexity zoo. And we looked at this sort of Chomsky hierarchy diagram on steroids, which is the picture I've been showing you all along, except much bigger and more detailed. And so from the classical languages at the top, it goes into, bifurcates into all these other complexity classes. Arrows here means set inclusion in the Venn diagram sense. So any class that points to an upper class above it is contained in it. Now, these containments may be proper or not. There's lots of theorems all over the place here, literally thousands of theorems. Okay, and we highlighted a few common classes that we know and love, that we talked about all the time. The set of all languages is up here. Then all the recognizable languages is over here. It's pretty close to the top because these are all the languages that we can compute using Turing machines, right? And then all the decidable languages are right below it. These are Turing machines that hold on all instances. It's still way up top in this diagram. There's a lot of stuff below. Exponential space is right here, and there's polynomial space right there. Anything above polynomial space is highly complex, requires more than polynomial space, exponential space or worse. And there's classes here that require more and more space and more time to compute. So we're usually not so much concerned with classes way up there because they're all infeasible. There's no way to compute them in this universe. There's not enough particles and atoms and picoseconds since the beginning of the universe to even put a dent in the difficulty of how long and how much space it takes to compute some of these languages and functions up here, right? So looking below that in the midsection of this diagram, which is probably the more interesting part, so again, there's polynomial space now on top. There's polynomial time, and deterministic polynomial time is where most of the interesting problems that we compute every day are, like addition, multiplication, matrix inversion, all sorts of heuristics, and sorting and searching and computational geometry problems, and of course compiling, and most of what we do every day is right there in this class here. But there's other classes above it. There's a polynomial time hierarchy. There's non-deterministic linear space. And most of the interesting classes that we can actually feasibly compute are below polynomial time, which means they're around this region here. So the empty set means nothing. These are all properties, by the way. How many get it? These are properties of languages. Okay, good. I'm glad most of you acknowledge that. There's the regular languages, the things that can be done by finite automata without any extra space, just with states and state transitions. Deterministic context-free is here. Here's general context-free, including non-deterministic context-free. There's a deterministic logarithmic space and logarithmic space for non-determinism. And there's a deterministic linear time, and there's many other classes here, and there's many other classes that are not even shown here in the complexity. So this is just the top couple of hundred, but there's 500 plus classes there. So basically, this is a more general picture of what I've been showing you all along, the extended Chomsky hierarchy. But for the purposes of this class, most of these classes of languages, most of these complexity classes will not be addressed, probably much to your relief, and don't even have time to even put a dent in those. But we did have time to mention most of these classes of languages, most of these complexity classes that I'll be showing you all along, right? The finite languages, the regular languages, context-free languages, polynomial time, non-deterministic polynomial time, polynomial space. And these are, in green, examples of languages from each of these classes that are not contained in the lower classes. Now, some of these containments are proper and some are improper. We don't know, for example, if p is equal to np. But we know that p is not equal to exponential time. And we know that polynomial space is not equal to exponential space. Those are simple corollaries of the space and time hierarchy theorems, the denseness theorems. So we know a lot about non-containments, but other non-containments are still open, or proper and improper containments specifically. And there's many other space and time hierarchies that are infinite, embedded all over the place. So that's sort of, again, the roadmap of where we've been, where we're going. Any questions about any of that? This is just kind of a quick summary of what we've been doing all semester long, really, not just the last few lectures. So having said all that, now we're going to focus on a particular portion of the diagram very, very narrowly. We're going to focus like a laser on this class NP here, non-deterministic polynomial time, and talk about NP-completeness. But keep in mind that every class here on this diagram has completeness theories associated with it and a completeness class of hard problems associated with it, not just NP. So there are problems that are p-complete. There are problems that are p-space complete. There are problems that are exponential time complete, and you can talk about all of that. In fact, there's even problems that are complete for these other more expansive classes out here. So for example, there are problems that are recognizable complete, and the halting problem is one of those, actually. The halting problem is the hardest problem for the class of recognizable languages. But now we'll talk about NP-completeness. So with that introduction, here we go, NP-completeness. So NP-completeness was co-founded by Stephen Cook and Cook-Levine in the early 70s. It's a study of tractability and what can be done in polynomial time, whether deterministically or non-deterministically. It's a study of computation versus verification. You all know that if you try to prove a theorem, it's often hard to find a proof. You might have to think for hours or even days and sometimes years or decades. In the case of Fermat's last theorem, it took 350 years to prove that one. But once you see a proof for a theorem, it's much easier to verify that the proof is true than coming up with the proof to begin with. And you've also noticed this in this class. If you see a proof or an answer by a friend or look it up on the web, it's much easier to understand that answer than to come up with it from scratch. So that is codified in the theory of NP-completeness as well, whether it's easier to verify something than to compute it to begin with. So for example, if I tell you that the product of two numbers is this result, right? If I take two primes, multiply them together, come up with the product and tell you, it's easy for you to verify if the product of these two numbers is equal to this larger number that supposedly is their product. That's easy to do using a single multiplication. But if I tell you, here's a number that's large, come up with its factors, factor it into primes that multiply out to this number without giving you the prime. That's much harder to do. And for many years, we didn't even know if primality testing can be done in polynomial time. And even now, we don't know if factoring can be done in polynomial time. But multiplication certainly can be done efficiently. So, okay. And it's a study of the power of non-determinism. So when you have computations that bifurcate like trees, instead of deterministic computations that is a single deterministic path, you have bifurcating computations where there's many next paths, and you take them in parallel, right? You can do more in some computation models, like push-down automata and others. So non-determinism seems to be helpful. Parallelism seems to be helpful. And non-determinism is studied by the theory of NP-completeness. It's also about encoding and transformations and reducibilities of some problems to other problems, and we'll see many examples of that. And you compare the power of polynomial deterministic computations to non-deterministic polynomial computation, and you look at the toughest problems in a class. That's why we call it completeness. So in the theory of NP-completeness, it exposes what are the hardest problems for a computational complexity class. If you can solve those efficiently, everything else collapses and is solvable efficiently too. Okay, so that's what NP-completeness roughly is in layman terms, but we're going to go technically pretty deep into it in the next lecture or two. So why do we bother doing that? So first of all, let's motivate it. So it saves time and effort in that you don't have to solve intractable problems if you know they're intractable. If you know that they will take exponential time or exponential space or worse, longer time than exponential even, there's no point in trying to come up with efficient algorithms for it. And over the years, many people have tried to solve intractable problems efficiently when it's not even possible. They wasted a lot of time and effort, and by a lot I mean billions of dollars over the years. Companies have tried to solve traveling salesman problem, Steiner tree problems, scheduling, packing problems, partitioning problems, knapsack problems, and these are all NP-complete. So there's no point in trying to solve something that is actually intractable. There's no point in trying to solve it efficiently. The best, what you should try to do instead is try to solve it heuristically. Try to solve it in a way that kind of quick and dirty gives you a good enough solution, not necessarily optimal, but you can work with it and move forward. So if you're FedEx, you want to solve traveling salesman in a heuristic, quick and dirty kind of a way, not necessarily optimally, still get reasonably good solution, maybe a few % away from optimal, but then you can still deliver your trucks and packages all over the city and all over the world every single day without having to wait a century of CPU time to get an optimal solution. It's just not worth it. So that's one huge advantage. You save money, you save effort, you save embarrassment of failing to solve things efficiently if they can't be solved efficiently and you know it. So you can also systematically build and leverage on the work of other people because all these problems are reducible to one another. So if you solve one of them efficiently, that translates immediately into efficient solutions of other problems. And we'll see examples of that. Right? And it kind of sheds light on how to transform problems into other problems and kind of illuminates the complexity structure of these classes of seemingly unrelated problems, but in reality they're very related just in subtle ways that we didn't think of before. And NP-completeness allows us to kind of look at them as whole groups of problems and process them as whole groups at the same time rather than individual problems one at a time, thereby wasting time and money and effort, right? And so it tells us when we should approximate things and when we should strive for exact solution. Right, so when you sort, you don't want to approximate a sorting algorithm because that can be done efficiently. Right? When you multiply or add, you don't want to approximate, adding or multiplication because again, that can be done efficiently. But for things like traveling salesman, bin packing, scheduling, Steiner tree problems, knapsack problems, colorability problems, those you do want to approximate because they can be done efficiently as far as we know, and chances are never. And we'll go into the reasons, the technical reasons why. It helps understand the concept of parallelism, and non-determinism is basically a model of parallelism. Non-determinism is unbounded parallelism. Parallelism is where the whole field of computing is going. Right now we have multi-cores, you have processors you can buy in your own laptops and phones. You already have multi-cores, 2 cores, 4 cores, 8 cores. There's even processors these days you can buy with 50 cores or 100 cores, and there's specialized GPUs that have thousands of cores, so it's highly parallel. And non-determinism now captures those classes of computers very, very well because they're so highly parallel. So it's a way of studying parallelism and the effectiveness of parallelism in computing. So we already mentioned it helps understand why verifying proofs seems to be easier than constructing them, and it illuminates kind of the nature of algorithms themselves and the actual computations that underlie the algorithms. And it gives rise to entire new theories of computation and mathematics and whole new proof techniques that weren't known before in the effort to resolve some of these open problems like P is equal to NP and hundreds of other open problems of which we saw many examples. So the math benefits, not just the actual results and the practical computations that arise from this. So we manipulate and reason about large aggregates of problems or functions or languages at the same time. It's much more effective than individually treating them separately. And it decouples the complexity classes from the underlying models of computation. So if 100 years from now we have some super duper iPhone, version 53 or whatever it will be, and we have supercomputers with, you know, 1 billion cores, not just 100 cores. The classes P and NP and P space and X time, they'll be the same for these future model of computation models, not just for the present ones. So any results and insights and relationships among problems and complexity classes that we derive today will be true in 100 years or even 1,000 years, or even for some alien race that we know nothing about. These are very robust classes. They apply to lots and lots of different computation models, both that we know of and that we haven't invented yet. You know, that's, so studying these relationships yields a lot of leverage and you get a lot of mileage out of these results. They don't become obsolete in 5 or 10 years. They endure, just like mathematics itself endures. And it tells you what the hardest problems in a class are, and it forges new unifications between different fields like computer science and logic and math, and now machine learning and other fields. And don't forget that, you know, an important reason to study anything, because it's fun and it's cool. That in itself is a reason. So with all that motivation, all these benefits, it dices, it slices, it bakes bread, it does all these things. These are good reasons to study NP-completeness. So let's begin. So this is probably the most important diagram of all, and we've seen this diagram before. It's about reducing a problem to another problem. So we have a set A and a set B. These are sets of strings. These are languages. And you have a mapping F that maps a string in A to a string in B. Okay, how many remember this diagram from before? We got a lot of mileage out of that when we talked about decidability and undecidability and problems which are recognizable and decidable and so on. So this is what we've done before. I'm just reminding you that F is a reduction of A to B. F maps members of A to members of B and non-members of A to non-members of B. And that's what it does. It's an if and only if. Okay, and we denote it as A reduces to B. And that also intuitively says A is not hardened, because if you can solve B, you can solve A efficiently. So if you can solve membership in B, you can solve membership in A by first translating over to B, solving the membership in B, and then you'd know the membership in A, because F preserves membership and preserves non-membership. So we've done this before, so this is just a summary. Here's the new twist on this. The new twist is now we'll force F to be polynomial time. So A will be polynomial time reducible to be if F, this mapping function, runs in polynomial time. Before, we didn't care. So before, we didn't care how long it takes to compute F. Computing F could be done in exponential time or super exponential time or linear time. It didn't matter. Now it matters. And things will become more subtle now that we're holding the clock on F and forcing it to be efficient. And by efficient, we mean within polynomial time. So F itself must be an element of P, the class of all problems solvable in polynomial time. So now we're watching the clock. F has to be efficient. It has to run fast, not just run any old way it wants. Okay, and things will become much more nuanced now. Okay, that we're putting a time constraint on F. So now we call F a polynomial time reduction of A to B. The notation stays the same, except there's a little p here showing the time bound on F is something restricted. It's not just any old time bound. It must be polynomial time. Okay? So a few things immediately follows. Here's the first theorem that immediately follows from this definition. If A polynomial time reduces to B, and B is decidable within polynomial time, then so is A decidable within polynomial time. Anybody want to explain why that is true? This is not a tough theorem. This is pretty straightforward. I mean, that's a big hint. Right? What do you say up there? Exactly. So it's the same process as before. You want to know membership in A, but let's say you don't know how, but you know how to compute F, and F is efficiently computable in polynomial time, and you already have a subroutine or a black box or an oracle to solve membership in B. So how do you solve membership in A? Well, take the string that you want to know if it's in A or not, map it over to B using this F that's easily computable in polynomial time quickly, and then use the subroutine for membership in B, and then automatically you'll know the membership for A for no extra charge. You won't be spending more time than polynomial. Okay, so if A is if B is decidable in polynomial time, so is A, because F is decidable in polynomial time. And at most, you'll compose the polynomial of deciding in B with the polynomial runtime of F, and polynomial of a polynomial composed is still a polynomial. That's one nice thing about polynomials. They're closed under not just multiplication, not just addition, they're closed under composition. If F is a polynomial function, then G is a polynomial function. F of G is also a polynomial function. It's not going to explode exponentially out of the blue on you. So polynomials composed with polynomials give you more polynomials of higher degree, yes, but they're still polynomials. And that's important, yeah.
What does mean the two polynomials times each other, not composed?
Good question. He's saying, wouldn't it be that the two polynomials multiplied together and not composed? What do you say?
If there are different steps, the transition is then followed by the operations for B. So you don't multiply, you don't do B steps F times. You just move to B, solve B, and back.
Yeah. So let's say I give you n numbers and and you want to sort them. So you want to sort them, and you can sort in n squared time using some, not necessarily very efficient algorithm like bubble sort, n squared time. So you want to sort the numbers, and it takes n squared time. But what if I give you, in order to sort, I transform the sorting input into some larger input, like an n cubed size input, and then I feed that to the sorting, to the bubble sort. So instead of n numbers, now I have n cubed numbers to sort, and I feed that to the sorting, and the sorting takes still quadratic time. So if I feed n cubed numbers to an n squared sorting algorithm, will it be the product of n cubed and n squared? How long will it take to sort n cubed numbers using a quadratic time sort? As a function of n, how long will it take? Will it be n to the fifth, n cubed times n squared? How many say n to the fifth? How many say something else? What is that something else? It'll be n to the sixth. So you're answering your own question. And that's what happens here.
But that's changing the size, not how long it takes to compute n squared to n cubed.
So he's saying, but that's changing the size. Well, when W gets transformed to f of W could be larger or smaller than f. But in particular, it could be larger. So f of W could be larger than f. So f runs in polynomial time, but I never said that f of W is the same size as f. It could be the square of f. It could be the size of f. It could be smaller than f even. But it could be f to the 10. It could, the size of W to the 10. Or this, so f of W could be much longer than W itself, but only polynomially longer, not exponentially longer. Why? Because if it's exponentially longer, it will take longer to compute than a polynomial time transformation, which is the bound in which f runs. So if f runs in polynomial time, it cannot produce something that's larger than a polynomial, but it can produce something that's larger than the input. And then you can get a larger instance. And it is a composition in that case. Now, it may be that it may not require all that time of the composition. It could be less, but it's at most the composition of the two things. At most. That's kind of a safe gross upper bound that we know we will not exceed. Okay, but it's a very good question he's asking. Okay, any other thing for now? So we're still pretty close to the definitions. Already things are not so obvious, as you see. Here's another theorem. If A reduces to B in polynomial time and A is not decidable within polynomial time, then neither is B decidable in polynomial time. Why is that true? Try to answer that in one word. It's that simple. Be brave, say something. Contrapositive, yes, we have a winner. Contrapositive, this is a contrapositive of that, right? If you say, if it's raining, then the ground is wet. That's one statement. The contrapositive is that if the ground is not wet, it can't be raining. It's basically the same statement reworded in a contrapositive way. Now, if you wanted to prove that without the contrapositive, let's say you didn't have the first theorem, so you couldn't contrapositive the first theorem to get the second theorem, and you wanted to prove the second theorem separately from scratch, how would you do that? If A reduces to B and A is not computable within polynomial time, then B is not computable within polynomial time either. How would you prove it from scratch? Again, you'd go back to the first principles of what this means. So if A reduces to B and A is not computable within polynomial time, we assume that it's not. Well, if B was computable in polynomial time, you can compute A in polynomial time by transforming it to B, solving it in B, and then you have a solution for A, membership in A. And then A will be solvable in polynomial time. But A isn't solvable in polynomial time or decidable in polynomial time, so neither is B can be done in polynomial time either. Otherwise, you'd have the contradiction that A is not doable in polynomial time to begin with. So basically, these two are the same theorem disguised, one is a contrapositive of the other. Any questions about these two theorems? So we're only going to get much deeper from here on out, not any easier. So if there's any questions, let's clear them up early so you don't miss out on important things because you had questions on things that happened before. Things compound heavily, as you know already, in this material on previous results. So again, the same caveat as before, be very careful which direction you're reducing from. Don't reduce it in the wrong direction, otherwise you don't get the result you're after. Now, both could be reducible to one another using two different functions, one f in one way and one f prime the other way, but one reduction has nothing to do with the other. They're two separate independent reductions that look nothing like each other, even though reductions may exist in both directions. So these reductions are directional, they're not bidirectional. Okay, so that's very important. So I'm saying it explicitly. So we transform problems to other problems using such F's, transformations. And we'll do that all over the place. You'll see lots of examples coming up of these transformations of problems to other problems. Okay. So for example, the problem of satisfiability can be transformed to the problem of colorability. And satisfiability is simply, I give you a Boolean formula involving x's and y's and z's, just some Boolean variables, and they're Boolean. So these variables can only acquire true and false values, not arbitrary values that they want, just true and false, yeses and nos. And the question is this formula satisfiable? Can you assign the variables to yeses and nos or trues and false values such that the whole question becomes, that the whole formula becomes true? Is there a way to do that? That's all. That's all in quotes because it's a tough problem to solve. As innocent as it seems, it's not so innocent. It's a really hard problem. Okay, it turns out. It's NP-complete. We will prove it's NP-complete. That's Cook's theorem, actually. So again, given a formula in, say, a product of sums form, and product means and sums means or. I hope that's clear for now, by now, because we've been using that notation all along. So in this context, plus means or, and a product like right there means and, logical or and logical and. Right? And apostrophes mean negation. So x apostrophe or x prime means not x. So if x is true, not x is false, and vice versa. All right, well, we can transform the problem of satisfiability, it turns out, into a problem that's also NP-complete, a problem of colorability, graph colorability. The problem of colorability is simply, I give you a graph with nodes and edges, and I ask you the question, if you can paint these graphs with, say, at most 3 different colors, red, blue, and green, say, is there a way to paint these nodes with red, blue, and green such that no 2 adjacent nodes share the same color? So it's like map coloring. In a map, you want to, if in a geopolitical kind of map, when you show boundaries of countries using colors, you don't want to paint the 2 countries that are adjacent to each other using the same color because then it'll be not clear where the border is. So different countries adjacent to each other, you want to use different colors for on the map, and then it's very clear where one country begins, one country ends, and so on. So that's graph colorability. So for example, a solution to this graph colorability, if you give it to a graph colorability solver, might come out like this. So here we painted the nodes with 3 different colors at most, red, green and blue colors, and no two nodes that are adjacent to each other that share an edge have the same color. If you haven't signed the attendance sheet, pass those back down and maybe sign them on the way down, but send them back to the front through the crowd. If you haven't signed the attendance, please do so. Okay, so that's graph colorability, and it turns out if you can solve graph colorability, you can solve satisfiability via a reduction, and the reduction is not obvious or simple. This F that reduces the problem of satisfiability to the problem of graph colorability is a complicated reduction. Cook came up with it in 1970. He got a Turing Award for that. In fact, that founded the entire theory of NP-completeness. So what Cook did was he did one of these, where A specifically was satisfiability and B was another problem. Okay? And we'll get to what the details of what he did are. It's really monumental. It's a monumental result. He showed basically that satisfiability is NP-complete. It's as hard as any problem in NP. And NP has a lot of interesting, ubiquitous, famous, and practical and useful problems that we need to solve every day. It's got lots of these problems in it, the class NP. In fact, it contains all of P. So sorting is in it, searching is in it, matrix multiplication is in it, and so on and so on. So this is a study of transformations, transforming things into other things. Any questions so far? Anybody recognize what this cartoon alludes to? See if you have a classical education. Yeah, Metamorphosis by Kafka. Right? Okay, so it's about metamorphosizing problems into other problems, like disguising them as other things, and then amazing things happen, as you'll see lots of examples. Okay, a couple more definitions. So a problem is NP-hard if every problem in NP reduces to that problem in polynomial time. Every problem in NP, not just 1 or 5 or 10 of them, but all of them. And NP has an infinite number of problems, or languages, if you will. Yeah?
I have a question about the transformation, the F function.
Okay. This right here.
It's defined there as polynomial time, but isn't it actually space limited? Because you pointed out that it could produce a result that's polynomially larger using that polynomial time. But if you then limit that space to, say, linear space, wouldn't that make it faster than the composition?
You could limit the space, but you don't want to. If you limit the space, you may be leaving some results on the table. So if you limit the time, you implicitly limit the space also, because you can't use more space than you have time to use. So if your time is limited by n cubed, your space that you're using in n cubed time ain't going to be bigger than n cubed. Because if all you're doing is just mallocing more and more and more space, touching more and more squares on your tape, and you only have n cubed time to do that, you're not going to be touching more than n cubed space while you're consuming your n cubed time and then forced to stop. So your space is limited by your time. And so if the time is polynomial bounded, so is the space implicitly, well, polynomial bounded too. But what you don't want to do is artificially bound it to only linear space, because then you lose some ways to transform into nonlinear, potentially nonlinear instances in B, and that may exclude you from general polynomial time transformations.
Well, what I'm trying to say is, isn't the input of FW into the D functions, which presumably solves B, a space-limited function instead of time? In other words,
No, it's time limited, not space limited. You can use as much space as you'd like within the time that you have. But as I said a minute ago, that still doesn't allow it to use exponential space. Because if you have polynomial time to consume, you can only consume polynomial space within that polynomial time. That,
but if you could manage to fit the results, FW into linear space, wouldn't that be faster?
yes, if you could, you may want to, but you don't have to. And even if it fits in n cubed or n to the 5th or even n to the 20th, that's still good enough to yield the result. One is still polynomial time reducible to the other, and that's okay. But in practice, you're right. In practice, you want to reduce it as much as you can, both in space and in time. In other words, you don't want to consume more than you have to. Right? So, for example, some sorting algorithms require n log n time, but linear space, linear extra space besides the input. So merge sort is one of those. You need an extra array to run merge sort, in addition to the array that the input came in. Quick sort doesn't require extra space. It requires 0 extra space, or constant, I should say, just a few variables, because it's an in situ sort. It's in place sort. With quick sort, you can do the pivot kind of rearrangement around the pivot in place in the original array. You don't need extra space. How many follow what I'm saying? So it's a better space usage for a sorting method. And it's preferable for that reason and other reasons too. So if you can use less space, sure, go ahead and use less space. But in this scenario, you can, but you don't have to. If you don't use less space, you're still good, as long as it's polynomial. And it will be polynomial space because it's polynomial time. So you cannot use exponential space if you only have polynomial time to use that space in. Right? In other words, if you're only going to be living for 3 billion seconds your whole life, and 3 billion seconds is a century, by the way. That's the entire lifespan. If you sometimes think about your life in seconds, it helps you prioritize how you spend your time and with who. But I digress. If you can only have 3 billion seconds, and you can only spend $1 a second at most, I mean, that's a lot. That's $3,600 an hour you'll be spending. That's a lot of money. You won't be able to spend more money than you have time to spend. If for every second that passes, you can only spend $1 at most. And sometimes you won't spend that dollar at all. You'll conserve money. So the amount of money it'll cost you to live will be less than the number of seconds you have left to live. That's what we're saying here. We're saying that you cannot use more space than you have time to use. I hope that example clarified rather than confused it. You may not have ever thought about your life in seconds. A year has 31 million seconds, by the way. What else? Any other questions? Okay, so it's about transformations. And a problem is NP-hard if every problem in NP reduces to it in polynomial time in the sense of this diagram that we just saw. Right? And a problem is NP-complete if it's NP-hard, and on top of it, if that problem itself is an NP. So it's two different constraints. So NP-complete is NP-hard plus this other relatively minor constraint that the problem itself that we're talking about must itself be in the class NP. It can't be outside of NP. Because if it's just NP-hard, everything in NP can be reducible to it in polynomial time, but it itself could be outside of NP. It could be in P space or X time or even some higher class, complexity class. So if one NP-complete problem is in NP, all of them are. All the problems in NP are in P as well, via these transformations. Because everything reduces to them in polynomial time, everything in NP reduces them in polynomial time. So if one of the NP-complete problems is in NP, through these transformations and compositions of these transformations, all of NP is in polynomial time. Which makes an NP-complete problem, in some sense, the hardest problem in NP. And it's not unique. There could be many other problems in NP that are also NP-complete that have this property that everything in NP reduces to them in polynomial time. So in terms of pictures, here's the class P, and this is a class of languages. So P is a property, P is polynomial time, P is the class of all languages recognizable within polynomial time by a Turing machine or by an algorithm. The type of P is set of sets of sequences of symbols. It's buried 4 deep, just like normal complexity classes. Here's NP containing it, and we don't know if it's a proper containment or not. That's the million-dollar question. Literally, worth $1 million from the Clay Institute. There's a bounty on this question. But it's not the easiest way to become a millionaire because it's been open for 45 years now. And many smart people have worked on it and failed. So here are the NP-complete problems, and satisfiability that we saw a couple of slides ago is one of those NP-complete problems. Right? And here, this is not a Venn diagram portion, so I put it in a dotted line because these NP-complete problems are not necessarily separate from P. So this oval is not necessarily disjoint from P. It could be included in P. If P and NP are the same, those three ovals will collapse into one. So this dotted line here of NP-complete problems, and that's an infinite set, by the way, this dotted line strays from the Venn diagraminess of this picture. I think I just invented the phrase Venn diagraminess, but I hope you know what I'm saying. Okay? Question?
So, in that definition of NP-complete, are those L's referring to the L of the previous definition, or are those supposed to be
So this L right here is one of those NP-complete problems. So it's color-coded. NP-complete is color-coded here. It's blue, but L is one of the problems in this set here that's denoted by NP-complete, and SAT is one of those L's. Satisfiability is one of those L's. The problem of satisfiability, or the language denoting all satisfiable formulas, all formulas that can be made true by some assignment of the variables. By the way, these formulas also be made true by all possible assignments, just one assignment. If there exists an assignment that makes the formula true, that formula is satisfiable. And you don't even have to give an assignment. You just have to give a formula that is true, that it can be satisfied by some assignment, and that's enough for inclusion in L, and L is SAT here. Yeah?
What I'm asking is, are those two L's down there the same as that third L prime up there?
Okay, I see what you're saying. Yes. You just found an error in the slide. This should be L prime, and this should be L prime. In fact, you know, this error is so important that I just specifically fixed it for you in real time. And you get extra credit for noticing that. Send an email to the class web form for that. I hope I didn't crash this program by fixing this error. Well, even if it crashed, you still get the extra credit, so how's that? So yeah, it's that L prime. Any other questions about any of that? All right. Let's see what we got here. Thank you, Microsoft. Oh, there's a Blueberry Muffin Turing machine. How about that? Oh, and there's a Roomba. I got one of those. Bear with me here. Ah, here we go. All right, any other questions? I'm afraid to take another one of your questions. Look at what happened the last time. Okay, but let's go ahead.
Clarification.
All right.
Is it accurate to say that NP-hard means some problem is at least as hard as NP, and then NP-complete is also no more hard than NP?
Yes, that's exactly what it means. If it's NP-hard, it could be harder than NP-complete. NP-complete is as hard as it gets inside NP. But things could be harder than that, more complex than that, take more time and space than that, like exponential time, exponential space, and you know, beyond that even. Good. Now you're getting it. All right. And there's co-NP, the complements of the problems in NP. And there's the co-NP complete problems like tautology. Tautology, it's always true, no matter what the assignment is. There's no way to falsify it. And of course, there's P-complete problems, and one of them is linear programming, and every class has complete problems for that class. So we don't know if P is equal to NP, but we also don't know if NP is equal to co-NP. All these classes can collapse together. We just don't know. Or co-NP can collapse to NP, but both of them may not collapse to P. So you can have it resolved in that way too. We just don't know again. Question? What broke? Okay, I'm afraid to do it again. But these L's here should be L primes, okay? Just like we attempted to do and didn't quite have that fix saved from last version to this. Accurate. But anything else for now? So that's what the neighborhood of these complexity classes look like, P, NP, and co-NP. But we do know something. We do know that P is equal to co-P. By the way, I don't want to be presumptuous. What is the complement of a language? That's a trivial definition, but somebody say it instead of me. The complement of a language is what? Everything that's not in the language, right? It's sigma star minus the language, right? So if you have a problem and you have an algorithm for solving it, how do you solve the complement of that problem? If you can solve the original problem deterministically, to solve the complement of that problem, all you got to do is take the answer and flip it. Take the bit and flip it. Turn a yes to a no and a no to a yes, be contrary, and then you're solving the complement of the problem. Now, for a problem in NP, that's not easy to do at all. Because NP says there exists a path, right? There exists a path to success. But the complement of that is not there exists a path to failure. The complement of that is for all paths, they do not lead to failure. There does not lead a path to success. The complement of some predicate P, there exists some very, some truth values that will make P true. There exists a solution that will make predicate P true. The complement of that is not there exists some value that makes it false. The complement of that for all values, P is not true. Okay, so to solve a problem in the complement of NP is not as simple at all as solving it in P and then flipping the bit. But for P it is. So if you want to solve a complement of a problem in P, solve that problem and flip the bit, and you got a solution for the complement of the problem. So, and that's also polynomial time, because flipping a bit doesn't change your runtime. That's just one extra constant operation after you do the exact same thing you did before. So P and co-P are the same class. How many get that? I only see 3 or 4 hands, so I better repeat it, I guess. But it's a question first.
Yeah, so just to clarify, these co-NP, these complement classes are, or properties are not the complement sets of the sets that contain the other property. In other words,
Yeah, so he's asking a good question. He's saying, at what level are we complementing? Are we complementing at the, because remember, the type of these sets is set of sets of sequences of symbols. Set of sets of sequences of symbols, namely sets of languages. So at what level are we complementing? At the highest level, namely we take all the languages that are not there, or do we take each language that's there, complement it, and throw it into the complement set one at a time? How many say it's the latter? Yeah, you're right. So we're not complementing it at the highest level, we're complementing at the next level over. We take the language, each and every language in this class, we complement each and every language separately and throw in together all these complements into one big set, and that's the co-set of the original, the complement of the original complexity class. Be careful about that, okay? Because now types are compound and they're nested 4 deep, and so when you say complement, be careful at what level you're complementing. Question?
So it just seems to me like a surprising result that if P is equal to co-P, then like a hardness of solving is going to be equivalent to it, despite having we just said that like it seems much more difficult to find something in code.
So for deterministic polynomial time, the 2 classes are the same. Now, there's a linear program. How many know what linear programming is? It's basically finding a solution to a large set of, or any set, not necessarily large, of linear inequalities. But the reductions, if you're going to reduce problems within P, in the reduction, in this F between A and B, you don't want to use polynomial time reductions. because the whole set is polynomial time to begin with. So if you're reducing polynomial time, sure, everything reduces to everything in polynomial time. Why? Don't reduce it at all and just solve it. So polynomial time reductions don't make sense within P. What you're going to do is use log space reductions. Now it becomes a lot more tricky to reduce, and the complexity of the problem is no longer overwhelmed by the complexity of the reduction. You don't want the complexity of the reduction to be larger than the potential complexity of the problem, otherwise it's not clear where the difficulty lies, in the problem itself or in the way you try to reduce it in some horrendously complicated way. And then that completely overshadows any complexity that the problem might have. So the reduction better take a lot less time than the problem itself, and then any complexity that remains is the problem's complexity, not the reduction's complexity. So very, very good point there. I should give you extra credit for saying that. Put it in for extra credit. Good question, good comment. So within P, you want to do log space reductions, not polynomial time reductions. That's typically what's done. If you didn't get that, don't worry too much about that, because we're not going to talk a lot about P completeness. We're going to talk about NP completeness, and the reductions will be polynomial time, not logarithmic space. All right, so here's SAT in more detail. You give a Boolean formula in conjunctive normal form, which means product of sums, where product is and sum is or, and apostrophes, hyphens like that, apostrophes denote negation, right? So here's a formula in conjunctive normal form, and the formula is satisfiable if and only if it can be made true by some assignment of the variables to some truth values. We don't care which. As long as one exists, it's satisfiable. So if you want to solve it brute force, how can you determine if a given Boolean formula with n variables, the formula could be very large. It could have 1 million variables and it could be 1 billion characters long. How can you determine if it's satisfiable or not? What's a trivial algorithm if you didn't care about space or time? If you just did it any old way you want, not efficiently, how could you tell if a Boolean formula is satisfiable or not satisfiable? Yeah, do all the combinations of the variables. In other words, write out the entire truth table of this formula with every possible value of x and y and z and w and all the other variables. Test each and every one in the formula to see if it satisfies the formula, if the formula comes out true. In other words, write out the entire gigantic truth table, and then you'll know. Right? How many lines of code will it take, roughly, do you think? Order of magnitude. 10, 100, 1,000, 10,000 lines of code to do that for a formula? A dozen lines of code will do the job, right? It's easy to do. So the algorithm is trivial if you're going to take a brute force approach. Now, here's the catch. How long will this dozen lines of code take to run for a given formula of n variables, roughly? No, they're Boolean values. Yeah, remember it's a Boolean formula, right? This is Boolean formula. Each variable is either true or false. That's it. It's not arbitrary integers. So it's not as bad as forever. I mean, it's bad, but not that bad. Right? How bad is it? 2 to the n, right? There's n Boolean variables. So the truth table will have 2 to the n rows in it, more or less. And 2 possibilities for every variable, and there's n variables, so 2 to the n different combinations of yeses and nos for the variable, and test each and every one through the formula, and then you'll know. So those dozen lines of code, short brute force algorithm though it is, will take exponential time to run. So solving any NP-complete problem in brute force, short piece of code is doable. They'll just take exponential time to run. The question is, can that be done in polynomial time? And that's the open question. We don't know how to solve satisfiability in polynomial time. If you could, P will be equal to NP, and you'll get your $1 million from the Clay Institute, probably an honorary PhD, and probably $1 million a job offer from Google, and the Turing Award on top. So it's been open for 45 years. But in brute force way, you can do it in just a few lines of code. That's the easy part. The hard part is to do it in polynomial time deterministically. Okay, so for example, x plus y times x naught plus z naught is satisfiable. For example, let x be 1 and z be 0. So the first term is satisfied because x is 1, so that makes the whole term true here because plus is an or and times is an and. X naught plus z naught is true because z is 0, so z naught is true. So whatever z naught is plus something else is true. So this is true, this is true, the whole thing is true for this assignment, end of story. So this small formula is satisfiable. I'm just giving you a trivial example. This formula is not satisfiable. It's a little more difficult to see why here, because to show that something is not satisfiable, you have to show that no combination of variables will work. But you don't necessarily have to test all 2 to the n combinations to see that it's not satisfiable. Why? Because to satisfy this term, x cannot be 1, cannot be true, because that term will be false, and these are ands. If that term is false, the whole thing is false. So x naught cannot be false, so that means x better be, x naught cannot be false, so x better be false. So x naught should be true. Z naught cannot be false, so z better be true. If, so z better be false, because z naught cannot be false. So if x is false and z is false, this term is false because x or z will be false because both are false. And so the whole formula is false. And so this can't be satisfied no matter what the x, the y, and the z are. How many can see that? Okay, so that's a counterexample of a non-satisfiable formula. I'm just giving you an example of one that is satisfiable, one that isn't, so you can see how it goes. All right, here comes the big one, the Cook-Levine theorem. Now, this theorem was published by Stephen Cook and Leonid Levine. He was Russian. It was published around the same time, 1970. And basically it says that satisfiability is NP-complete. Everything in NP reduces to it. So both these guys showed it independently. They didn't know each other, and both published it in 1971. They didn't know about each other. You know, what happened historically is it took 10 years for people to realize that both of them came up with the same result 10 years ago in 1971. It took until like the late 70s or 1980 or so to realize this happened. And interestingly, Stephen Cook was denied tenure at Berkeley. It's probably the worst tenure decision in Berkeley's history because 10 years later he won the Turing Award for doing that. And he's one of the best theoreticians on the planet. But at the time, I think it was still tenure track, and people didn't quite understand the magnitude of the result. It was so earth-shaking and esoteric and groundbreaking, and invented an entire new branch of computer science, NP-completeness, that people didn't recognize the forest for the trees, so it took a while. But he invented this whole theory that we're talking about now. Leonid Levine, on the other hand, he was a student of Andrei Kolmogorov, the famous Russian statistician, mathematician who invented, co-invented information theory, basically, and pioneered large portions of statistics and probability theory. Except he did this in Russia during the height of the Cold War, so that his paper was very obscure. It was written in Russian, and in Russia at those days, money was not widely available for researchers and research, and so people tried to conserve the number of pages in the publication, and he crammed his entire paper into like a page and a half. And it was very, very dense. Never mind that it was written in Russia, and most Westerners did not know Russian or attended Russian conferences, and most Russians were not allowed to travel outside the Soviet Union to attend Western conferences. So there's this big chasm of disconnect between Russian and Western scientists and mathematicians. So Stephen Cook's paper looks like this. It's a multi-page paper, single author, and published in 1971 in the theory of a symposium of the theory of computing, which is one of the top forms for computer science theory. And he says right up front, out of the gate, he says, it is shown that any recognition problem solved by a polynomial time-bound and non-deterministic Turing machine can be reduced in this F kind of A to B business that we showed, can be reduced to the problem of determining whether a given proposition formula is a tautology, in other words, satisfiability. So he knew exactly what he was doing. He was showing that satisfiability was the hardest problem in NP, that everything in NP could be reducible to it. And of course, the paper goes on for another dozen pages and gives the reduction and all the details. And it's all correct and all very insightful and so on. Here is the first page of Levine's paper, except it's not just the first page, it's all of it. This is the entire paper. And now, how many in the audience can read Russian? I know some do. Maybe you can make sense of what it says there, but even if you know Russian, even if you're a mathematician who studied mathematics in Russian, it's still very hard to understand this paper. It's extremely dense. But it's been looked at very carefully over the years by experts, and all the details are there, very, very densely explained. Just like in Cook's paper that takes, over a dozen pages to do the same. So he gets a lot of credit, and now it's called the Cook-Levine theorem. but for 10 years it was called just Cook's theorem. And of course, Cook got the Turing Award in the meantime before Levine was even discovered to have co-invented this. So sadly, Levine didn't get much credit, except now we call it by his name too. But he didn't get the Turing Award. He should have co-won the Turing Award for this, if we knew that he did this actually. So more of the story here, it's you should write very clearly, succinctly, in a way that is self-explanatory, that makes sense, that's easy to understand. Don't make it too obtuse and too convoluted. And it's important how you present your results as well as having good results. And by the way, in episodes of The Simpsons, there's in the background little mathematical humor jokes like P is equal to NP kind of floats around. Here's Euler's formula also floating around there. But Simpsons have mathematicians on staff whose job it is to come up with these little mathematical gems and nuggets in terms of humor. And your mileage may vary because most audiences probably won't quite appreciate these nuggets, but they're there nevertheless. Okay, so that's Cook's theorem. And there's a classic book by Garey Johnson. It's on the website for extra credit. You can go through it and tell me what you got out of it. But it's sort of the encyclopedia of NP-completeness. It gives you hundreds and hundreds of NP-complete problems, and the reductions that were used to prove that they're NP-complete, and their relations to other NP-complete problems, other problems that are even not NP-complete, and it's an encyclopedic treatment of the subject. And there's other books on NP-completeness too, but that's an early one. It's from 1979, and it's still very, very valid today as it was then. Remember, these theories are machine independent, and they withstand the test of time very, very well. These theories don't change as the decades proceed. Just like number theory. Number theory, invented in the 1500s or the 1600s, or even by the Greeks, is still very valid today. The Pythagorean theorem holds today as it did in the time of Pythagoras. It's not going to all of a sudden become invalid or useless. Same with these kind of theories. So don't let this 1979 date scare you. This book will always be up to date in some sense in terms of what it teaches us. And this cartoon is taken right out of the book. By the way, here's an example of how useful this theory is. Before then, if your boss in some company told you, solve this problem, whether it's traveling salesman problem, bin packing problem, scheduling problem, knapsack problem, Steiner tree problem, any one of the problems that NP-complete, and people have tried to do this, solve them efficiently, and they all failed. And now we know the reason they failed is because these are all NP-complete problems. They're harder, they're at least as hard as anything in NP. But before that, your boss will say, solve this problem. You have 3 months and $1 million budget, hire a couple other mathematicians, go. And you'd come back in a few months and say, I couldn't solve it efficiently. I don't have an algorithm that's polynomial-time. And your boss will kind of look at you and think, oh, maybe you're not that intelligent. Maybe we made a mistake hiring you. And it'd be kind of awkward. Except that neither you or your boss knew that there's no point in trying to solve it efficiently because it's NP-complete, and if you could solve it efficiently, not only you'd solve that problem, you'd solve everything in one fell swoop in NP efficiently, and not only your boss should be happy and you should get the next pay raise, you should probably, be the director of research for the entire company and probably paid $1 million a year because you're so smart, because you knocked out everything in NP simultaneously. And so what they asked of you by solving this individual problem is too monumental a task. So after NP-completeness was invented, what you could tell your boss is not, oh, I guess I couldn't do it, I guess I'm not smart enough, sorry. What you can tell your boss is this: I can't find an efficient algorithm, yes, that's true, but neither can any of these famous people that have tried to show that satisfiability is NP-complete or that P is equal to NP, and hundreds have tried, and they're all, Fields Medal, kind of Nobel Prize winning mathematicians and scientists, and they all failed, so it's not surprising that I failed too. I'm no worse than all these Nobel Prize winners and field medalists that failed and famous mathematicians. That's a lot better thing to tell your boss. Of course, before you can say that to your boss, you got to prove it's NP-complete. Because if it's not NP-complete, if it's something as simple like sorting or binary search or, that you better solve efficiently and not have some brute force exponential time algorithm for sorting. Right? Then something else is wrong. So that's one more advantage of NP-completeness. It kind of indemnifies you against embarrassment or possible demotion or firing from a company if you can point to the problem that you're trying to solve and prove it's NP-complete, or look it up somewhere and somebody else may have proved it's NP-complete, and then the burden is no longer on you to try to solve it efficiently because Nobody else could either. Otherwise, P will be equal to NP. Okay, how many get this strategy? Good. So remember that. It can save your job one day. And in the past, people didn't know to do this. In fact, the theory didn't even exist, so people couldn't do this. And a lot of people tried to solve all sorts of problems separately, individually, across thousands of companies all over the planet for decades. And they all failed, wasting billions of dollars and millions of man-years. And nobody knew why. Now we know why. Because these problems are as hard as anything in the class NP. All right, so backtracking from that, let's prove Cook's theorem. And when we prove it, I'm going to give you the idea of the proof, not necessarily all the details. So we already said what satisfiability is. Given the Boolean formula, come up with a satisfying assignment if there is one, and determine if that formula is satisfiable. Okay, so here's the proof idea. Right? This is the proof that Cook's paper was about. This is the proof that founded and gave rise to all of NP-completeness theory, and then, of course, all these other completeness theory for all these other classes. All right, here goes. So we're going to take an arbitrary, non-deterministic polynomial time Turing machine and an input, and we're going to transform this machine and this input into a Boolean formula in such a way that that machine will accept its input if and only if that formula is satisfiable. Right? So we're going to construct an F, one of those transformations. Right? So remember before, we had a machine and an input, and we wanted to know what this machine does on this input in terms of the halting problem. But now, we want to know what this machine does on this input, given that it's a polynomial time non-deterministic machine. And yes, we can simulate it in exponential time by following all the non-deterministic branches of the computation and doing it deterministically, and then we'll know if it holds or doesn't hold on this input. But we want to do it in deterministic polynomial time. And we don't know how to do that. We know how to do it. We know how to do it in non-deterministic time or in exponential deterministic time by massive simulation. In other words, we're trying to solve the halting problem on an arbitrary machine and an arbitrary input where this machine is non-deterministic, but it still runs in polynomial time. So we're trying to solve the halting problem for a polynomial time-bounded non-deterministic computation or non-deterministic Turing machine. Now, it's no longer undecidable because if it runs in non-deterministic polynomial time, and we know that polynomial, all you got to do is simulate it for that long, and then you'll know what it does or doesn't do within that time. But how do you do it in polynomial time, deterministically? That's the question. So what we'll do is we'll take this machine in that instance, arbitrary instance, transform it into this new problem, and that new problem will be an instance of satisfiability, and this function f of this transformation of this pair into this new instance of satisfiability would have the property that this machine will accept its input if and only if this Boolean formula will be satisfiable. So if there is an algorithm, a black box, an oracle, that in polynomial time can tell me if a formula is satisfiable or not, we can exploit that into telling us whether an arbitrary polynomial time-bounded Turing machine will accept its input or reject its input, and we'll do it within the same time that we can solve satisfiability. And if we can do that in polynomial time, we can determine arbitrary non-deterministic polynomial computations, what they will do and not do, in deterministic polynomial time. In other words, this is an arbitrary computation in NP. How many get that? It's an arbitrary Turing machine, an arbitrary input, and it's polynomial time-bounded, and it's non-deterministic. So this represents an arbitrary computation in NP, any computation in NP. And this transformation that transforms it into a Boolean formula will work no matter what the machine M and the input W is, in a way that preserves the acceptance and the non-acceptance of M and W, and whether this Boolean formula that results from this transformation F will be satisfiable or not. It's an if and only if. So if we can solve satisfiability efficiently, we can solve arbitrary, non-deterministic computation, polynomial times computations efficiently as well, as efficiently as we can solve satisfiability. In other words, everything in NP here, because this is an arbitrary computation, non-deterministic polynomial times, arbitrary computation in NP, everything in NP reduces to satisfiability. which means satisfiability is NP-hard. Everything in NP reduces to, remember the definition of NP-hard 3 slides ago, everything in NP reduces to in polynomial time, that makes it NP-hard. It's also NP-complete, because satisfiability is in NP. That part is easy to show. How do you show that satisfiability is in NP? How can you show that you can have a relatively straightforward, non-deterministic polynomial time computation that resolves satisfiability, that tells you if a formula is satisfiable or not satisfiable? This part is relatively easy. What's your non-deterministic algorithm for satisfiability? Yeah.
For the x1, have one choose it to be false, one choose it to be
Yes, excellent. For every variable you choose, take the first x, or x1, branch 2 different directions. In one branch, say it's true, in the other branch, say it's false. And in the next branch, below that, pick another variable, x2. Branch yes or no, left or right, false or true, and keep branching. So after n branches, which means the width of the tree is 2 to the n, you'll have all possible ways of assigning the variables to yeses and nos, all n variables to yeses and nos. And at the bottom of this tree, take the result that led you there of the yeses and the nos and do what? Check to see if that set of decisions of yeses and nos actually leads to satisfiability by plugging it into the original formula. So at the end of every branch, you got to check. So you can guess and then check, guess and verify. Okay? How many get this algorithm? And if it verifies, if the formula comes out true after a series of guesses, report yes and succeed and go into a final state and say, I'm done, you know, this formula is satisfiable. If it doesn't pan out, you don't have to do anything. Because non-deterministic acceptance, if there exists a path to success, you're good. Not all paths must lead to success. At least one of them does, you're good. Okay, so that's a non-deterministic algorithm for satisfiability. And all NP-complete problems have non-deterministic polynomial time solutions. And most of them have linear time solutions. This was a linear time algorithm. How many see linear time here non-deterministically? Because it was just a linear number of guesses. And the time is the height of the tree, not the width of this non-deterministic computation tree. The width is exponential. The height is not just polynomial, it's linear. Linear is a very small polynomial. Okay, so that's the strategy here. So how do we do this transformation? The transformation is the hard part. F will be difficult to describe. Not that difficult, but it's not trivial. So we're going to create a Boolean variables. The Q's will be denoting that at step I, the machine is in state K. So here's the machine, here's its state Q sub K, here's the read-write head pointing to the tape. The H Boolean variables, these are all Boolean variables indexed by I and K. And at step I, the machine's read-write head will point to the kth cell on the tape. And this will be true if and only if H sub I comma K is true. If not, it'll be false. S sub I jeb K is another sequence of indexed Boolean variables that mean at step I, the machine's tape cell number J contains the symbol K from the alphabet, the kth symbol from the alphabet. So all these Boolean variables encode the state of the machine. What's on the tape at every instance, every cell on the tape, which state it's in at that moment of the computation, from moment 0 to moment when it actually finishes after some polynomial number of steps, because it is a polynomial time bounded machine, right? It says so right here, polynomial time Turing machine M. So there'll be a lot of Boolean variables encoding all the different configurations the machine can be in terms of its states and in terms of every single cell on its tape, and wherever the read-write head is, that's encoded too, okay? So there's a lot of encoding going on in these Boolean variables. But having these variables is not enough. You got to connect them in the right way. And the way to connect them in the right way, for every time step I, you want to say the machine is in exactly one state. So only one of the state variables better be true at time I, and the others better be false, because the machine cannot be in multiple states at time I, non-deterministically, just in one state. The read-write head can only scan one cell at a time. The read-write head cannot scan 17 different cells at the same time. So you encode now a bunch of clauses in this growing Boolean formula that says at time 1, the head can scan cell 1, or at time 1, the machine can scan cell 2, but not cell 3 and 4 and 5 and 6, or the machine can scan cell 3 at time 1, but not cells 1 and 2, and then 4 and 5. And there'll be a lot of clauses, a huge number of clauses. But you encode this restriction that the read-write head can scan at most one cell at one moment using all these clauses. How many can begin to see what's going on here? Yeah. So the machine at time 0, and by the way, you're going to say all cells contain exactly one symbol. So if at time 1, the first cell contains the first symbol, at time 1, the first cell cannot contain the second symbol. So you add clauses for all of those, for every time, for every cell, for every symbol. There'll be, yeah, a lot of cells, a lot of symbols, a lot of clauses. But the point is there'll be a polynomial number of them because the machine only goes through a polynomial number of steps. It's a polynomial time-bounded machine. So you'll have a bunch of clauses, and at time 0, the machine is its initial state, and at time p of n, the time it takes to run, the polynomial runtime, the machine will be in its final state, and now you got to encode all the transitions in the right way. So if you're in time number 17 step, and the read-write head is pointing to cell number 15, and that symbol in that cell is symbol number 3, and you're in state number 7 in the control, then the next transition step must be one of whatever the transition function specifies, and not all the other options that it doesn't specify. And you got to write all those tediously down one after the other. There'll be a lot of them, but only a polynomial time. So this is the F. This is the transformation of an arbitrary Turing machine on an arbitrary string into a Boolean formula. And this Boolean formula resulting from this will be satisfiable if and only if this machine accepts that string. So if you can solve satisfiability efficiently, you can solve arbitrary polynomial time non-deterministic computations efficiently. And so all of NP reduces to satisfiability, which makes satisfiability NP complete. That's Cook's theorem. Whew. Deep breath. Any questions? All right, next time we'll summarize this again because that's a lot to take in. But read about it in the book. Finish the homework by this weekend. There'll be another homework soon, and we'll see you next time. Bring me these sign-up sheets. Oh, thank you.
Is it okay if I sign?
Yeah, go ahead.